Hello and welcome. In this video, we'll be discussing how we can use our regression models for predicting new observations. So one of the most useful properties of the regression approach above, say, a correlation is the ability to predict something that hasn't necessarily happened yet. There are a couple of caveats, though, so as we address this, do keep these in mind. First of all, prediction has to be for the people represented by our sample. So if I did a sample in a whole bunch of undergraduate students and I'm trying to predict something for working professionals, then that might not work very well. Also, and we've discussed this before, you should be wary of extrapolation or predicting outside of the range of the data. If I studied something about people who make, say, between $5,000 and $8,000 per month, then that result won't extrapolate very well to people who make $1,000 a month or to people who make $50,000 a month. So being careful of and this is kind of with point one, but making predictions about the people who your sample represent, not just in terms of the generic characteristics, but also in terms of the specifics of the X values that you studied. You should also, and this is going to be another thing that we'll discuss in this lecture set, make sure that assumptions are met. So one obvious one that we have already talked about is that the relationship follows the relationship that we're specifying. In simple linear regression, we're assuming that the relationship is a line. And so if you look at a plot of the data, you should say, yeah, a line seems like it works there. And if it doesn't seem like it works there, you shouldn't use your line to predict something that will follow along that pattern. It's worth remembering our predictions are essentially looking at the line and picking a point on the line for a particular X value, and that's what we're going to predict. So our line is our prediction, and you can just kind of trace your finger along it to figure out what you're going to predict. We'll talk about doing that a little bit more precisely, mathematically precisely, as well as with a little bit of confidence and accuracy using some confidence intervals. But it is important to understand no point is exactly on the line. Just like our line doesn't perfectly fit all the points in our sample, our line's not going to perfectly match for a prediction. Our prediction is going to be off. And yeah, that's just going to be off a little bit. But with that said, on average, the predictions should be right, given the caveats above. And in addition, as I referenced just a moment ago, we can build intervals around predictions if we build our predictions mathematically, such that we can be confident that the predicted value will fall within that interval with a certain amount of confidence. So we've actually already been doing some predictions in regression, believe it or not. We've been doing that when we made the y hats as part of our calculation in inference. Essentially, what we're going to do for prediction with a new value is we're going to take the X value we're interested in. We're going to use a new notation for that. We're going to call that X star, and then we're going to predict what we think is going to happen in the outcome for this new independent variable. And we're going to call that prediction Y star hat. So we're going to take a new value and predict on the line what that value is going to be associated with. And again, while you're doing this, and certainly if you're doing this in an applied setting, you need to make sure you're keeping in mind the caveats below and also remembering those caveats, those caveats before, and also remembering that those caveats from before are not the only caveats. There's a ton that goes into contextual interpretation and appropriateness in predicting from regression. So just keep an open mind and remember all of this is a component of the logical argument. So to the degree that your logical argument is failing, this isn't going to work well. All right, so let's try a couple examples. So for instance, let's start with the equation y equals 3 plus 5x. And we want to predict y, or find y hat star, when x, our new data value, is 2. So to do this, I simply plug 2 in place of x. I get 3 plus 5 times 2. 5 times 2 is 10. 3 plus 10 is 13. Yay! Not too bad, right? All right, so y equals -10 minus 3x. Go on and pause the video. Try it if you want. Predict y when x star is 5. Plug in 5. I get -25. So that's it. Predicting with regression, that it seems kind of anticlimactic a little bit. We're predicting new data points using regression models that have optimized to have the best data fit for the sample points available using the ordinary least squares method. Again, it sounds fancy when we're predicting this. And in a way it is. I mean, remember that in this case, it's not the prediction that is the steps that we just did that's really the work. The work went into figuring out what is that perfect equation, what is that optimized equation above. So the work went into building those equations more than it does into the making the prediction itself. But yeah, once you have the equations, prediction with them is pretty easy. So as we said before, these predictions are our best guesses. So for that first bullet, when X star is 2, 13 is my best guess of what the outcome is going to be when X star is 2. But I know it's going to be wrong. Like, it's not going to be perfect. So the next step is to construct the reasonable range for our prediction to account for this uncertainty. So I'm going to build some intervals. But here's the thing. The nomenclature is going to be a little bit confusing. And that's because there are actually 3 types of intervals that have to do with regression. The first one is a confidence interval for parameter estimates. So think the confidence intervals we did in the inference section. Remember, we built a confidence interval for the intercept and a confidence interval for the slope. That's exactly what we're talking about here. We already did that. That one's done, but that's a term confidence interval, and that's a distinct type of confidence interval, the confidence interval for parameter estimates. There's a second type, though, a confidence interval for prediction. So I have a prediction value, and I make a confidence interval around it. Now, this confidence interval is going to be regarding the mean value, that is, the average outcome if I predict at that level. There's a third type of confidence interval that we'll call the prediction interval for prediction. And this is going to regard predicting an individual value. So let's say I'm going to make a prediction on my regression line, and I want to predict it for a specific case. That actually gives me a different interval than predicting it on average. And so we'll talk about that distinction. Again, we're about to elaborate on the last 2. Those are the new ones that we're talking about in the prediction context, but sometimes those first 2 can get really confusing. And so I wanted to explicitly list out all the different terms here and talk about that. Specifically, that there's 2 different types of confidence intervals. This seems super confusing, and in a way it is, but in practice, it's not too bad. Essentially, if you're looking at regression, like the regression line, the confidence interval is probably going to be talking about the first one. If you're talking about the slope, the confidence interval is going to be talking about the first one, right? The confidence interval for the slope, or the confidence interval for the intercept. But if you're discussing a specific predicted value and you start talking about confidence intervals are going to refer to that second type, the confidence interval for a prediction. So the context will usually give it away, but it is confusing that there's 2 types of confidence intervals. And unfortunately, this isn't like just this course or just Dr. Florin being crazy or this textbook being crazy. This is kind of how it is. This is kind of the general nomenclature. All right, so let's jump into these different types. The first one we're going to talk about, confidence interval for prediction. Now, this gives a reasonable range for the average predicted outcome to fall in. So think about if I'm looking at a marketing campaign and I'm trying to predict the profit. And so I look at a marketing campaign that costs $8,000 and I'm trying to predict the profit. If it's the case that I'm trying to predict the profit for a specific campaign, this one is not the one to use. But if it's the case, then I'm about to run 10 campaigns at $8,000, and I want to see the average return for all 10 campaigns, like what's the mean of the group, then this is the one that we would use. So this is the mean predicted value of a group. Another way of thinking this is essentially what we're doing with this confidence interval is finding where the line could fall. So if you think about the line, the sample line is not perfect. This confidence interval for prediction is essentially where could the line or the average value fall. It's another way of looking at it. I will say the misuse of this, which is extraordinarily common, leads to too small of an interval, or too liberal of an interval. Think about, I am saying with 95% confidence the profit's going to be between here and here, and that's only 50% correct. Like, that's the type of problem you run into when you use the wrong one. This can be built using the point estimate, standard error, and critical value. In this case, the point estimate for the predicted value is going to be the predicted value, y hat star. And this is the regression equation with x star plugged in, that new value, like we did on the previous slide. The standard error for the confidence interval for prediction is going to be denoted S sub y hat star. That is the standard error for y hat star, the predicted value. This is going to be S, which is from our inference slides, times the square root of 1 over n plus x star minus x bar. That is the predicted x value minus the mean x value squared, divided by that same sum of x minus x bar squared that we've been using essentially through this whole lecture set. The critical value for this is going to be a 2-tau critical value, as we typically associate with confidence intervals. And it's going to use our degrees of freedom for the error, n minus p minus 1, as many of our other t values have. Now let's jump into something, and we'll just define both of these in our practice problems together. But the next one, which is the prediction interval for prediction. For most cases, people, when they're trying to do prediction using regression, this is the one that they want. They're trying to predict the next thing. I want to know, if I ran this marketing campaign at $7,000, how much profit am I going to get when I run this at $7,000, like for one specific instance. When we're trying to do that, predict an individual value, we don't use the confidence interval for prediction. We use the prediction interval for prediction, this one. Again, this is relatively rarely used in my professional experience, with people leaning towards confidence intervals, but using them as if they are prediction intervals. And there's a distinction there. All right. So it's worth noting, what's a big distinction? This one is always going to be wider. It's always going to be less precise than the confidence interval for prediction. And this is correct. It's because individual variability varies a lot more than mean variability. So mean variability is going to be relatively small compared to the extra individual variability that we have to take into account when trying to predict an individual value. Often this width is undesirable in the sense that people, clients, bosses, etc. don't like it. But remember, this is how wide it needs to be to accurately be that confident. So if we're trying to be 95% confident, this is the correct width of the interval. It's a lot wider than you want it to be, but this is the correct width when predicting individual values for that particular problem. Again, this is typically done in comparison to the confidence interval. And sometimes people will say, I want to use the confidence interval because it's narrower. It's not that you can't do that. It's that you're just wrong. Your error rate is higher, potentially much higher, than if you used the correct interval that has the correct error rate. So could you use a smaller one? Yeah, you'd just be wrong more often than you say you want to be. If you want to be 95% confident and you used a smaller interval, your true confidence should maybe be closer to 50% or 20%, or maybe something even lower than that, depending on how narrow your interval is. But if you want an interval that is correct the amount of times you say it's supposed to be correct, it's a 95% confidence interval, and you are actually 95% confident in it. Prediction interval tends to be the one to go when you're trying to predict an individual value, which, again, for me and in the clients I work with, is almost always the case. For this case, the point estimate's the exact same, y hat star, and that's the regression equation with the new data point put in. The standard error is denoted something a little different because we want to keep the standard errors different between the confidence interval for prediction and the prediction interval. So the notation for the standard error for the confidence interval for prediction was S sub y hat star, and that kind of covered it. So for a prediction interval, we use S sub pred to stand for prediction interval. This is going to be S times the square root of 1 plus 1 over n plus x star minus x bar, quantity squared, over the sum of x minus x bar squared. I want you to notice that for this standard error, this looks almost identical to the one on the previous slide. The only difference compared to this and the standard error for the confidence interval for prediction is the 1 plus under that square root. Otherwise, these are identical. Incidentally, that 1 plus is what accounts for the individual movement that makes the interval wider, and having the 1 plus in the standard error ensures that mathematically it will always be wider because this is just a larger number every time. As before, we do the t distribution for the critical value, but it is worth noting here, we are no longer under the central limit theorem. Remember, with all of our other predictions, we're using the capability, that's the wrong word. We're using the attribute of data, the theorem that essentially says that when we're looking at means are always distributed as a normal distribution, and our t-distribution is just an adjustment based on not knowing the population standard deviation. The trick, though, is now that we're talking about individual data points, the data point of individual data points is not necessarily normally distributed. So unless we assume individual data points are normally distributed, this interval might very well not be correct. Now, if we assume individual data points are normally distributed, this is going to be fine. But again, normally we've been able to do a lot of our stuff under the central limit theorem because we've been talking about means. But when we're predicting individual values, it's worth knowing that we're straying a bit off the ranch here. That is that under that central limit theorem, which is what we've been able to do most of this class under, we're not really under that when we're trying to predict individuals anymore. All right, so let's try this with our marketing profit example. So I've got my predicted regression equation, and let's say I'm trying to predict the profit if my marketing campaign costs $8,000. In the scale of my x variables, remember it's in thousands, so my x star would just be 8. So I'm going to try to build both a confidence interval and a prediction interval. Looking at these equations, I'm going to need some information. I'm going to pull S, my x bar, my sum of xi minus x bar squared, and my t. All of these I've found previously, but I need to get all of these and pull them from my previous work. With these, now I have to find 3 new values: y hat star, s sub y hat star, and s sub pred, which are my standard error of confidence interval for prediction and standard error for prediction, respectively. All right, so let's solve for these values, and I'm just going to shove it on this slide here. Y hat star is going to be 2.1317, and you'll notice that that 8 in parentheses is my x star value. I plug in my new x value, and I get my predicted y is 2.1317. On the left-hand side here is my standard error for the confidence interval for prediction, and plugging all my numbers in and solving, I get 0.4743. On the right will be my standard error for the prediction interval for prediction. Again, you see these equations are so similar, save for that extra 1 plus on the right-hand side equation, the prediction interval for prediction standard error term. And I work this out to get my standard error for prediction to be 1.3415. With both of these, now I can plug these in to get my confidence intervals. So my confidence interval for the y hat star, this is my confidence interval for prediction. Again, point estimate plus or minus critical value times standard error. Plug in my values, I already have these, and then I hit enter and I get 0.9125 to 3.3509. Let's contrast this with my prediction interval for y hat star. I plug in my values. Notice the only thing here that changes is my standard error term between the left and the right. On the right-hand side, I'm using the standard error for prediction. On the left-hand side, I was using the standard error for the confidence interval for prediction. Plugging in my values, I get a different value, negative 1.3167 and 5.5802. All right, well, let's talk about what does this mean? I got 2 different confidence intervals. I got 2 different stories. One was the confidence interval for prediction, and one was the prediction interval for prediction. So what are these things talking about? So for the first one, I'd expect the average profit of an $8,000 marketing budget to be roughly between $1,000 and $3,300. Okay, so that's the average if I did that. On average, if I did it again and again and again, I'd expect the average return to be somewhere in there. Now, if I did a single one, remember, a single one can vary a lot more than an average. So if I did a single one, I'd expect the profit for any specific $8,000 campaign, any one, to be between a $1,300 loss and a $5,600 gain. Note here that's a big difference in interpretation. And again, if I came to my boss with the left one, assuming that meant the right one, that is, I assume 95% of the time we're going to make between $1,000 and $3,300. And let's say we came back and we lost $900. My boss is going to be really irritated and wonder how that happened. Now, if I just did the calculation correctly, I can realize that a $900 loss is well within that reasonable range. In fact, in the reasonable range, up to a $1,300 loss is considered reasonable with these numbers. So it's good to be careful of my conclusions here. And again, prediction intervals tend to be the direction that people want to go with this type of information. Again, in this case, if, say, a loss is unacceptable, these two would lead to very different conclusions if I didn't distinguish between their correct interpretations. So for this case, if I'm trying to predict a specific $8,000 campaign, the prediction interval is the appropriate one. If I were just trying to look at, in general, I'm about to run a bunch of these, what's the average return I can expect on these, that confidence interval for prediction would be the correct one. But again, typically we're trying to say, hey, I'm going to run one of these. What do I think the return's going to be? And because it's just one, there's an additional level of variability associated with that makes that interval wider. But again, we have to widen it to be correct, to be have that correct error rate associated with it. All right, team. Well, it's your turn. So go on and give this a shot with your example. Again, as before with everything, feel free to go back in your notes or rebuild. Yeah, go on and pause the video, give this one a shot, build the confidence interval for prediction and the prediction interval for prediction with X star equals 5. Pause the video, give it a shot, and I'll see you on the other side. All right, let's check into it. Going back to the calculations we've done previously, I found S is 3.1264 for this example. X bar is 3.9875. The sum of X minus X bar squared is 67.76. And T for this is 2.4469. So now I need to find Y hat star, S sub Y hat star, and S sub pred. All right, so Y hat star, I get 84.3869. Hopefully you get the same thing. S sub Y hat star, I get 1.1703. And S sub pred, I get 3.3383. So hopefully you're getting the same things I am. Here's my work up here. Pause it if you want to check if you missed something. Or, of course, let me know if I missed something. I hope not. But yeah, these are the values that I'm getting for my a standard error for my confidence interval for prediction and standard error for prediction. You'll notice the standard error for the confidence interval for prediction is less than half of the standard error for the prediction interval for prediction. Again, it's going to give me a much smaller interval. Plugging these values, I get my interval 81.5 to 87.25, give or take, for the confidence interval for prediction. And for the prediction interval for prediction, I get 76.2 to 92.5, give or take. So here, if I were looking for the average for many times with 5,000 students, I'd expect between 81,500 and 87,250. Well, if I'm looking for a specific time, say next semester we're going to have 5,000 students, I'd expect anywhere between 76,000 and 92,000. Again, very different intervals and potentially involving very different planning strategies if I want to make sure I'm covering at least the bottom end there. All right, ladies and gentlemen, well, in this video, we've covered how we can do prediction using regression. We went from simple prediction, where we just predicted a single value based on an input value, but then we expanded to talk about how we can do confidence intervals for prediction, what that means, and prediction intervals for prediction and what that means. Again, in general, I recommend the prediction interval for prediction if you're deciding between the two. So anyway, thank you so much, ladies and gentlemen, for sticking with me through this video, and I will look forward to catching you in the next one.